Namaste. Welcome to this channel, Chemistry Made Easy by Dr. Ashok Mulik. We were discussing this topic, that is theories of acids and bases. And today we are going to see the frontier orbitals and acid-base reactions. So up till now we have seen variety of theories which are explaining the acid-base behavior, such as Arrhenius theory, Laurie-Bronsted theory, solvent system concept, as well as Levy's acid-base theory. And next to these theories is this frontier orbitals and acid-base reactions. So first of all, we must know what are these frontier orbitals. Frontier orbitals are those, you can observe here, the HOMO means highest occupied molecular orbital. So if you see this NH3 molecular orbitals or atomic orbitals here, you will find that this A1 atomic orbital is occupied. So these are also containing electrons. This is also containing electron pair, and there is no more electron. So this is highest occupied molecular orbital. So in addition to this, or there is no more electron in higher energy molecular orbital. So this is called HOMO. In this case of H+, there is this 1s orbital of H+, which is having higher energy and there is no electron. So this is called a LUMO. So in such case, their interaction takes place during the acid-base reaction. The interaction takes place between this LUMO and HOMO, or HOMO and LUMO, and therefore during the acid-base reaction or any other reaction, the reaction is expected or taking place between the HOMO and LUMO, and therefore these two orbitals are called frontier orbitals, and these are actually involved in the variety of reactions, or in this case the acid-base reaction. So we can have such number of examples in which these frontier orbitals are involved, but in the present context we are discussing the formation of this reaction, that is H plus NH3 gives NH4 plus. So we are discussing here the formation of NH4 plus in terms of the frontier orbitals, or else the example of acid-base reactions. So first of all, we must know what are these, what is molecular orbital obtained from ammonia molecule. If you see this molecular orbital diagram for the formation of NH3, you will see here there are atomic orbitals of nitrogen which are shown in this direction. So nitrogen has 7 atomic number, means 7 electrons, out of which 2 electrons are present in 1s, 2 electrons are present in 2s, and 3 electrons are present in 2b. And 1s is inner orbital, that is not a valence shell, so that is not involved in actual reaction. So that is why we are not shown these 1s orbitals of nitrogen. In case of the 3 hydrogens, there are 1s orbital in each atomic orbital. So we are saying that the 3 hydrogens provide 3 1s orbitals, and these are together called group orbitals. These are together called group orbitals. So there is a group of 3 1s orbitals. So there are only 3 electrons provided in these group orbitals of 3 hydrogens. So during reaction or during the formation of ammonia, there is linear combination between these 2s and these 1s orbitals, group orbitals. So for this purpose, certain fraction of can see. So in order to see this, there is formation of NH3. So there are 4 bonding molecular orbitals. So bonding molecular orbitals are 4. Out of these, first lowest energy is of A1 symmetry, and since it is representing this or formed from the linear combination between 2s and this 1s, it is named as 2A1. So this 2 represents this second 2s orbital, and it has A1 symmetry. So this molecular orbital has A1 symmetry. So these are giving the sigma bonding or A1 symmetry orbitals. Then there are 2 p orbitals. There are 3 p orbitals, out of which one is pz orbital and 2 are px and py. So this pz orbital has sigma, means sigma orientation or A1 type of symmetry. So this is represented with 3A1. So 3A1 is obtained from pz of this nitrogen and 1s of this hydrogens having matching symmetry. So that is A1 symmetry of this. Means all these 1s orbitals contribute the A1 symmetry orbitals, or fraction, we can say fraction of these A1 symmetry orbitals for the formation of this 3A1 molecular orbital. And these are 2 molecular orbitals having one E symmetry, means E symmetry type orbitals. So these are obtained by px and py, linear combination between px and py with these 1s orbital group, 3 orbitals having appropriate symmetry. So there is appropriate symmetry, matching symmetry is the most required. So this will produce 2 molecular orbitals having E symmetry. And similarly there are these antibonding molecular orbitals resulting from linear combination between 2s and these group orbitals of 1s, 4A1 and 2E, E symmetry antibonding molecular orbitals are produced from px and py of this, and the matching symmetry is bonding molecular orbitals are produced here. So in this way we can get the molecular orbitals for NH3 which are 4 bonding and these antibonding molecular orbitals, 4 bonding and these antibonding molecular orbitals. So these are in all 4. Means here actually here is no correction, that there are these 3 these orbitals, means 2 orbitals. So there are such 2 orbitals. So you will find that there is this 2s and 2p, 1 2s, 3 2p, means in all there are 4 and plus these 3 means 7, 4 plus 3, 7 orbitals. So they will result also equal number of molecular orbitals. So out of these 7, 4 are bonding in nature and 3 anti-bonding in nature. So this is about the NH3 molecule. So the same is shown here in the formation of NH4 plus. So NH3 and this NH3 is same. So on this side we have represented the atomic orbitals or the orbitals, molecular orbitals of NH3 on this side. So it has this A1 symmetry orbital. This has one E symmetry orbitals. So you will find here 2, they are E symmetry orbitals. This is A1 symmetry orbital and this is A1 symmetry orbital, 4A1, and this 2E, E symmetry orbitals. So after linear combination between this H plus and these orbitals of NH3, that is A1 symmetry orbital of 1s of hydrogen H plus, and these orbitals, that is this E symmetry, A1 symmetry, this A1 symmetry, and these 2E symmetry orbitals of ammonia will undergo linear combination between the appropriate symmetry orbitals. So they will produce this bonding molecular orbital, which is directly transferred from this MO system to this MO system, and they are having A1 symmetry. Now here you will find that these are two A1 symmetry orbitals which are contributed by NH3. But here you will find that the A1 symmetry orbital is also there, and it is having very close to, means lower in energy to this group orbitals, but it is very close to this E1 E symmetry orbitals. So because of this, when this is filled, means when it occupies electron, this 3A1 symmetry orbital when occupies electron pair, the energy of this A1 symmetry molecular orbital is lowered, and that is merged into this group of E symmetry orbitals, and as a result of this, together they are showing that tetrahedral symmetry orbital. So there are three such tetrahedral symmetry orbitals which are obtained from combination, means addition of these 2 plus this 3. So there is A1 symmetry orbital and E1 E symmetry orbital. So they are having different symmetry. But after the formation of NH4, the different symmetry orbitals are converted into tetrahedral symmetry orbitals. So this is important change in the symmetry. So you will observe here that there is, this is NH3 molecule having electron pair, that is lone pair. So this is Z axis and it has C3V symmetry. But after reaction with H plus, there is change in symmetry with the formation of tetrahedral structure. So this is like CH4 structure. So this is tetrahedral shape of this molecule. So this is observed here, given here with tetrahedral symmetry. So there are 3 molecular orbitals of NH4 having tetrahedral symmetry, which are occupying all these electrons. Then this antimony molecular orbital A1 symmetry and T2 symmetry are vacant. There are no electrons. So this is the case of formation of NH4 plus in this way. Now, so this is about the you should know that in this case, this 3A1 symmetry orbital which is occupied filled with electron pair is called the highest occupied molecular orbital, and this is empty. 1s orbital having A1 symmetry is LUMO, lowest unoccupied molecular orbital. So during the formation of NH4 plus, the HOMO and LUMO interacts because there is very small energy difference between this HOMO and LUMO. So the electron pair of this 3A1 symmetry, as we have seen here, and these 2 molecular orbitals of E symmetry are here coming together at same energy level. So this electron pair also moves here, and these 2 electron pairs are also moving in the tetrahedral symmetry orbitals. So this is the formation about the interaction between HOMO and LUMO. Now we will see the acid-base interactions in different types of acid-base examples. So here you will find this in this figure, HOMO, LUMO interactions. So we have taken here water as a reference compound. It is named as A, and it has this homo. It has this homo, and this is also lum. You can say that this is also a lum. So everywhere this will have this is homo, this is lum. This is homo, this is lum. Similarly, homo, lumo, homo, lum. So you will have this variety of the levels or atomic orbitals which are participating in acid-base reactions. So if we take this water, it has this homo occupying electron pair. This is vacuum, and there is you should consider the comparable energy difference between these water and other species when we carry out the reaction. So these are the homo and lumo for calcium. These are the homo and lumo for Cl minus. These are the homo and lumo for Mg2 plus, and these are the homo and lumo for F2. So we have presented that this water as A, calcium as B, Cl minus as C, Mg2 plus as G, and F2 as E. So we will discuss here acid-base reactions between these A and these variety of species. So when we are considering water as a reference, so it behaves as oxidant, acid, as base, as well as reductant. So we will see the examples. First is water as oxidant. So if we see that this reaction twice H2O plus Ca, you see H2 plus twice H minus and H2. Here water removes electron from this calcium. So it is called oxidant. As a result of this, calcium neutral atom is converted into Ca2 plus, and as a result of this, H2O gets reduced with the formation of this hydrogen gas and twice OH minus. So here you will find that the species, that is, this is acid, means water oxidant, and this is reductant, you can see. So this is because here calcium has this electron pair at much higher energy level than this LUMO. So it is directly moving to this here LUMO. But here you will see that the electrons are transferred. The different energy difference between this LUMO and this boron is much higher. So because of this, you will find that the transfer of electron takes place completely. So electrons of calcium are transferred to this water. Now in the second reaction, water behaves as acid. So you will see that Cl minus. So relative energy levels you can find between water and this C, that is Cl minus. So Cl minus, energy levels of Cl minus and this water are comparable. So here the Cl minus, this water acts as an acid. So Cl minus takes up or gives electrons to this H2O, which shares electrons with this water. So it gives a coordination compound like ClH2ON, and the charge is transferred completely on the complex. Then here the next water molecule can behave like a base. So here magnesium has vacant this s orbital. Magnesium has vacant s orbital which can accept electron pairs from water, and therefore it gives a complex MgH2O6 plus. Here therefore water acts as a donor of electron pair, and here water acts as acceptor of electron pair. So you have to remember the difference between the behavior of water as an acid, water as a base. So here water accepts electron pair, here water donates electron pair to metal ion. Similarly, in fourth case, you will find that the water acts as also a reductant, means it reduces other substance. So here water supplies or donates its electron pair to fluorine. So as a result of which this neutral species is converted into anions, 4F minus, and these hydrogens are donating their electrons, so they are converted into H plus. As a result of this, oxygen is also here converted into O2, that is molecule, neutral species. So here this species, each species is behaving in different manner. So here in case of magnesium, you will find that this LUMO is lower energy than this HO. So this electron pair is moving here easily in the LUMO. Then in case of fluorine also, the electron pair of water is also easily moving into this LUMO. So the fluorine is reduced, and therefore water is called here a reductant. So these are some examples of acid-base behavior of water. So with this we will stop our discussion and we will go for next point in the next lecture. So please subscribe to this channel and press bell icon and like button. So thank you very much.